So folks, in this section we're going to take the familiar concept in Calculus 1 of finding maximum and minimum values of a function, and we're going to extend that to the multivariate case. Throughout this chapter we're going to restrict ourselves to only a certain type of multivariate function. We're only going to be considering multivariate functions of the form f mapping from R2 to R. We're not going to do this for the end variable case. There does exist a theory for higher dimensions, but we're not going to get into it in this class. Okay. So again, what we're thinking of is we've got the one dependent variable z, and that is dependent upon the choice of the domain values x and y. So one way we could think about this is we could have the domain space x comma y. And so if we were to take something, let's say we take this point right here, a comma b in the domain space, that point gets paired a y-coordinate, or a z-coordinate, which may be out here. This would be the ordered triplet a, b, f of a, b, where we get the height value from the function. Okay. So what I'd like to do now is let's go ahead and just label some of the common terrain features that we're going to study in this section. And these definitions really shouldn't be a surprise. Let's go ahead and state some of them. I'm going to call this point right here, we're going to call a local maximum. Okay. And this point right here will also be called a local maximum, but it's a special type of local maximum that we will elaborate on. But what do I mean by a local maximum? Well, if I imagine this as being maybe in the positive quadrant here, maybe this is the ordered pair, this has the domain input x naught, y naught, and it outputs some f of x naught, y naught, that if I were to take that domain input x naught comma y naught, and I were to put any sort of open disk around it, let's pick a color we haven't used, any sort of open disk around it, that if I were to take any input value from within that open disk and look at its output, notice that all of the output values would be below that particular input. Okay? So for any other point that shows up here, its third coordinate, let's call this the point maybe E, F, and G, its third coordinate right here is going to be less than that third coordinate there. If I can do that for any size open disk around this point, I could make this even smaller and smaller and smaller. If I can do that, then we're going to call that point a local maximum. Similarly, so here we've got a local maximum. Similarly, we're going to use the terminology a local minimum, which again means that if you take any domain value near that, sufficiently near that point, and plug it into the function, you're going to get z values that are larger than or equal to the z value that you get at that point right there. This point right here is also considered a local minimum. But there are 2 points here we can elaborate on. We're going to say that this first point here, while it's a local maximum, it is also a global maximum. Which means if I take the entire domain of this function here, if I look at the output values, the z values that I get when I plug in any ordered pair x comma y, all of those z values are going to be smaller than or equal to the z value that I get when I plug in that domain value at that point. Similarly, this point right here, as best I've drawn it, let's get that out of the way, as best I've drawn it, this point right here is also a global minimum, besides being a local minimum. And that just means that of all of the points in the domain, all of the xy ordered pairs, plug them into the function, they all spit out z values that are either equivalent to that z value or larger. That's what we mean by a global minimum. So there's the definition, folks. Please read through that, take some notes on it, and we'll pick up in the next video.